Yeah, I don't know if you've seen that account, like Weird DALL-E. They have like crazy images, that they put on, like the Demogorgon from Stranger Things holding a basketball. That is like insane. That is like so cool. And you go through it and there's like
Oh my
amazing
God.
things that are like so fun.
You're listening to Gradient Descent, a show about machine learning in the real world, and I'm your host, Lukas Biewald. Boris Dayma is a machine learning consultant and a longtime Weights and Biases user. In fact, he started using us in such early days when I knew all of the users. Boris has gone on to build a model called DALL-E Mini, which is a model inspired by OpenAI's famous DALL-E project. And somehow DALL-E Mini has just captured the imagination of the world to the point where I've seen it in New Yorker cartoons. I see it all over my Facebook feed. It's just an amazing piece of work. And I'm really excited to talk to him about it today. So, I mean, maybe taking a step back for people who maybe aren't familiar with DALL-E at all, could you talk about what DALL-E is and what DALL-E Mini is and DALL-E Mega and how you've been working on this?
Yeah. So DALL-E is that it came from that paper from OpenAI of beginning of last year, and it was really amazing. And actually, the first time I saw it was a tweet you posted about it, and I replied to that tweet, and I was like, I'm gonna build that, and I was like, this is so cool, and I was like, I'm gonna build that. I want to build that, and it was basically OpenAI had done the first like impressive image generation model that you would type any prompt and you would do something that looked actually cool. Because before you had like image GPT or whatever, which would do like something very tiny. You have a bit the idea, but it would do something more complex, like the avocado armchair, which was cool at the time. Nowadays, the avocado armchair is just something simple. Like, it's nothing impressive anymore. It's crazy. Like a few months ago, I was still very happy when I had good avocado armchair. um, yeah, so that's where it came from, and basically, like in July of last year, I wanted to build it. I didn't do anything for 6 months. Um, I read the paper quite a few times. I don't know how many times I read it. I read it like a ton of times, and I didn't understand much to it. And at some point, like Hugging Face and Google, they organized like a hackathon where you had to build something cool in JAX, which is like a programming framework from Google, and you would have those cool computers from Google, those TPU, VM, and I was like, okay, that's an opportunity to do something cool. So I was okay. I'm gonna try to build the replication of DALL-E in terms of the results, and it turns out that it worked pretty well. I researched a lot of the papers. Some people joined in the team too, and somehow the program had pretty cool results for such a short time frame. And then I continued.
Can you describe how the program works? I mean, it really feels like magic. Like, how is it actually set up?
I know. It felt like magic for me for so long, and I think even if I read the paper again now, each time I read it, I learn new things. Um, so basically, the way it works is you have like good model right now for NLP, which transform text into text. So, for example, let's say for summarization, or let's say for translation, going from English to French. And you are trying to do kind of the same thing, except instead of going from English to French, we want to go from English to an image. But it's almost like the same. It's just a translation. Um, so the way you do it, when you do text to text, you encode each text become a token. It's just a number, a unique number, and you try to predict that sequence of number, and each number corresponds to some text. And we try to do the exact same thing, except that each number corresponds to a patch of an image. So that's all it is. So first you need to try to create an encoder that's going to transform that image into a sequence of numbers, the same that a tokenizer for text would do. And once
Wait,
you have that,
sorry, can you slow down a little bit for me? So
oh, sorry.
you have an encoder that's taking text, right, and turning it into some kind of encoded vector.
Yeah, that's
and
right.
then the vector goes into a decoder that creates the image.
That's right.
But what did you say about the batches? Or
Yeah, no, that's exactly right. Except typically when you have the decoder, it would create a number that corresponds again to text. Now
Oh.
you want that number to correspond to some kind of image.
Oh,
so
I see.
so
Right.
so you could try to do RGB, like the pixel values, the problem is there would be too many, so it wouldn't be very efficient. That's what Image GPT was doing, and that's why they had like maybe it was 16 by 16 squares, or so it would be very very small and it's very limited. But instead, what OpenAI did, each number corresponded to a patch. So, for example, one number can correspond to a green patch. One number can correspond to a blue patch with a yellow dot in the center. They all correspond to something more complex.
I see.
So you train basically a separate model that's completely independent and that's trained separately and frozen later, that learns how to create those patches. And the goal is because you're limited in vocabulary, maybe you can create only 10,000 different patches, 16,000 or something like that. I think it's what is used commonly. So what you do, you want to create the patches that are going to be used the most often, the one that are the most relevant. So you have a model that basically is trained to find those patches. It looks at a lot of images and tries to encode it into a code book where, in the end, when you reconstitute the image, it's as close as possible to the original ones. Once you build that, once you're able to go from image patch to a number, it's the exact same thing as doing a translation.
And are the patches in like a grid, like a 2x2 grid?
That's right, they're in a grid. So often, I think for me, the picture is divided. Each patch is about like a 16 by 16.
Oh, wow. It's amazing you don't notice that. Yeah, those are big patches.
So it's not completely independent patches because it's a unit. So with the convolution, there's a bit some overlap in the middle, which makes sure that you don't see those patches.
I see.
Yeah.
So they're kind of blended together between.
Exactly.
I see.
Yeah.
And then, interesting. And so it's the same as like with like from the attention is all you need paper with the like attention encoder is kind of identical to that translation model. Is that right?
Oh yeah. It's very similar. So DALL-E, what they do, it's just GPT. So you have GPT, it reads the text. Then there's like a special token, maybe. I mean, I don't have exactly the details because the code is not released on the paper. But the paper is very detailed, but it's missing a few of the small details. So it's like you have all the text, and then you have the encoding for the image at some point. And so it predicts, and at some point there must be a special token that says, hey, now it's an image. So it switched to another modality. My model is slightly different in the sense that have the encoder. It's like a translation model where the encoder and decoder is separate. So the encoder will read the caption, and then the decoder will do the image and will be causal. And the idea was that it would be maybe more efficient.
And now with like a 1D like string of text, I kind of understand how you feed back each individual one into the decoder and it looks at the previous words. But how does that generalize to like a 2D image? How do you do that?
So the 2D image, actually, you just put the patches next to each other. You don't consider the 2D. So it's actually an issue too, because basically when you predict the image, it's almost you predict from top left to right, to bottom right,
Oh, is that right? Just like in a line by line?
Yeah, that's what is done. So that's a problem because if you mess up at some point, it influences the entire rest. That's a limitation that diffusion models don't have, for example.
And now, like, how do you actually train this? Because I would think it would generate images that would typically be just totally like, each image actually is quite different from like an RGB value. So how does the training work?
So the training, the way it works is like the image, you will first encode it into a sequence of numbers. And then your text will be also a sequence of numbers, typically when you have your tokenizer. And your input basically is going to be those numbers for the text, and the output is going to be those numbers for the image. But the image encoder, it's frozen at that point. You don't train it. So you just go from numbers, a sequence of numbers, to another sequence of numbers. So then what you do, you have that decoder. It will predict the logits. It will predict what are the numbers for that image. And it's decoder that goes from 1 to 1, and the attention looks only at the previous patches, and it will predict it. And then you have the ground truth because you know what is the real image. So then you're gonna calculate cross entropy. You're gonna calculate the loss, the same that you would do with another problem, to see how wrong you were. So basically, it's kind of strange because you have a caption that will say a cat in the field. And then you have a ground truth image. And basically, the goal is to predict that ground truth image. It's a bit counterintuitive that it works because there's so many possible cat in the field.
Right.
And it could be right. And you try to predict only one specific one, which is that specific image you're looking at right now. But somehow it works. Somehow it learns to eventually, to associate concept, to minimize the probability. Like the simple way to think about it is, let's say if you want to predict a view of something by night, or the view of something or the beach during the day, the model will know that, okay, it should probably be dark images at the top. It's gonna be black because it's the night, or it's gonna be very dark blue. So I'm gonna just increase the probability for those tokens. And if you say during the days, like, it's probably going to be blue. Maybe there's some sky up there, and then when it outputs the next tokens, it already knows the previous ones. So you have part of the image, you need to predict the rest. It's easier to predict.
Oh, so when you're doing the prediction, you're feeding in part of the ground truth image and then trying to complete it?
So you're feeding the entire image, but basically each token sees what is before itself. So, for example, the first patch doesn't see anything, but the second patch sees the one that's before.
Not its prediction. It's the one that actually was before?
Sorry?
The second patch token sees the ground truth patch, not the first predicted patch.
You're right. The second patch sees the ground truth of the first patch. And let's say when you predict the second bottom half, it already knows the exact ground truth of the first top. And it also sees the prompt. So, it's the prompt also is supposed to help.
Right. But I guess I would think, like, if you were just, like, say you a cat at night or something.
Yeah.
If I was going to guess, like, just a whole image of that I want to be closer from, like, an RGB space,
yeah,
I could imagine it might be better to just predict, like, gray than, like, drawing a specific cat in a specific point.
Yeah. So that's actually a huge problem. That remember, I was playing with colorization before, and you predict gray is like the best, the most chance. If you don't know anything, just output a gray image.
Right.
But in that case, the loss is cross entropy on tokens. So you don't have an advantage in predicting gray because you have the same loss for being correct or for being wrong depending on the color. Saying gray or blue while it's red, you have the same loss there.
Oh, so you're predicting the probability of the next token, and there's only a set of. I see.
Yeah.
I see.
So you don't have the problem that it's gonna show like black and white images, or it has to predict something, and a color it may as well.
I see. What was it like to build this? Like, what kinds of issues did you run into? I would think this would be one of those things where it's just incredibly hard to debug when the program's not working.
Oh yeah. It is quite hard because you don't know why it's not running and what's happening. I think what was good is the first version, the DALL-E Mini. Maybe we were lucky. Somehow it worked well, pretty fast. And we thought a bit of those details. Like seeing the last token, you can have a little mistake, like you have an offset of one token, or you have little params, and it doesn't work. And we used a pre-trained model, so we used just a summarization model. And we decided, okay, the decoder retrains from scratch. Now it needs to predict the images. And what was good is it actually worked pretty well fast. So when I worked later more on the larger model, you have always a baseline. Is it getting better or worse? But there was some bugs that I spent 2 weeks or more to understand what was happening, why it doesn't work.
Can you tell me about one of them?
One difficult one was like, let me try to think of an interesting one. An interesting one was like, I was trying to use alibi, which is like the way you encode the position embeddings and all. No, sorry, I messed up. I was trying to use sync former. So sync former is a certain way of adapting the transformer where you normalize the token and all. But it's used for encoder models. But for decoder, basically, you don't realize it, but you have some information that leaks through the next token. So I would have my loss that was going very well, very fast to close to zero, and I had no clue why. And it's just when it normalizes, it gets some information of the future, and that was really hard to understand why that type of model didn't work. But the biggest challenges were actually, when you make it larger, training those large models is very, very hard. And when I first had the small model, I was okay. It's gonna be easy to have a large model. I'm just gonna add more layers and train it on bigger computers or for longer, maybe a bit more data, and it's just gonna run. But unfortunately, it didn't work, and that was a bit sad. And first, you have to be able to split the memory well across all the devices. It's not very easy because one model doesn't necessarily fit on one device, so you need to spread the weights across the other devices. Jax has cool features to do that, by the way. That was very, very helpful to do that. But then you have the model that becomes unstable. You have peaks that happen randomly. It starts well the first hours. You have your loss that goes down, and you're so happy. And then suddenly you have like big peaks, and like, oh, okay, fine, I'm going to restart before. And it's like, okay, now it went through, but like 5 minutes later, another peak, and it was like really, really hard. On that level, something that was cool is like as I was training it, I was making my reports, on weights and biases, and I was sharing them online all the time since I was working on that. And what's cool is like the community on Twitter and all got very engaged with it, and they were like so helpful. Actually, I don't know if I would have been able to build it with that success without having shared all the journey, because like I had like few key elements that helped make the model better, and that were shared by replies on Twitter. Like, oh, maybe you could try that. Like the optimizer we use, like distributed shampoo, and it just came kind of randomly through Twitter, or super conditioning from Catherine Cross, and it was like a bit random things that I discovered along the way just by sharing that training publicly. So it was very beneficial for me.
That's amazing. So you were sharing weights and biases reports on Twitter and getting feedback?
Oh yeah. I was getting feedback, and I think little by little there was interest. I was showing the new predictions, and then I was like, okay, I wanted that little demo online so people can play with it a bit. And some people were already engaged, like, oh yeah, I see, it's better at that, or it's bad at this, and it would give me idea on what to correct. And having it open helped me a lot, because in the end, it's almost like it feels like it was not just my work. I got like free advice from everybody too, so it was really good.
It would be fun to see all the weights and biases reports. I wonder if you could like make a collection of the history
I did.
reports. Ah, cool.
Yeah, if you open, I have a main report basically, and I link to all those reports. I link to all the main ones. If I had to link to all of them, there would probably be like 50 reports or more, And there's some I did just for myself that I wouldn't share because they were messy. Like the things like sometimes like, oh yeah, you have a conclusion, you do some test, and like, okay, it's important maybe to use drop out or not to use, or weight decay has no effect, but you forget it when you do so many experiments. You forget why you don't use it. And so I would always go back to my report. I know I had those experiments somewhere, and I would type a line like, oh, here, this is the runs, those are the runs that show that you shouldn't use that. And it was actually very convenient for me to see why I take some decisions, or why the previous code ran but not now. What was the difference between those two runs? It was major help.
That's really cool. Do you feel like there was enough in the DALL-E paper to really reproduce it, or did you feel like there were things you had to like key things you had to learn along the way to really get the thing to work?
So the DALL-E paper actually provides pretty clearly the main ideas. And the main ideas, like there's the last model we didn't talk about, but there's one model that's going to encode the image. The one I use is not the same as the DALL-E, is actually one from timing transformers. Some other people adapted it and added some GAN loss in there, some perceptual loss to make it a bit better. So the prime, it creates those weird artifacts that we have sometimes on the faces and all, versus the original one. What it would do something blurry. And then there's that model that needs to predict the next tokens. So for OpenAI, it's like a kind of a GPT model. Me, it's more similar to BART, which is encoder decoder. because I thought it could be maybe more efficient. And then they have that clip model that actually was released. They released little by little a model larger and larger, but that's a model that has like revolutionized a lot of the um, a lot of the research in multiple modalities, and that include like text and images, and now audio. People are adapting it for 3D, but it's that model that basically it will tell you how well it learns how well a text and an image match. So it will give a score. You give a text, you give an image, and it will give a score based on how well it believes they match. So for example, when you use the demo, we output more images than the 9 that you see. We output maybe 16, maybe more if there's not too much traffic, which never happens nowadays. But then over those 16, we have clip look at them, and it chooses the 9 that it thinks are the best, and it actually improves the quality quite a bit.
Oh, interesting. So there's outliers that you don't get to. You
Yeah,
don't get to see.
the ones that are really bad, typically it will find them like, no, don't show them. It's not worth it. But so the paper actually has those ideas, which are the essential ideas. Then it's missing some details on how it's trained and all. There's a lot of details. There's some things a bit that are missing. But overall, it's a good base enough to build something. I wish, like I could have just run the code immediately and train it. Actually, in a way, I'm quite happy. How to say it? In a way, the fact that it was not released motivated me to learn how to build it. I don't think I would have learned how it was built if I didn't have to try to build it myself.
That's cool. I mean, how sensitive is the performance to the details of how the model works, in your opinion? Like, I always wonder this. I don't know if you have a thought here, but like when I look at the attention mechanism, we tell ourselves a story about, the 3 vectors that get generated and how they're multiplied together.
Oh, yeah.
But I kind of wonder, like, how much do you think that the specifics of that really matters?
So I think there's some details that whatever you put, it works. It's like when I started to do machine learning, I know you have to do a convnet to detect cats and dogs. And I remember I was like, oh, I'm going to try to build my own model. And then you're like, what depth should I put? How many layers? I'm like, I'm going to put 12 here, and then I'm going to put 36, and then I'm going to put less and more. And I would put random things for no reason. And whatever you do, it works. Like on simple
Right.
model, whatever you do, in the end, it kind of works. I think, there's so many configurations where it would work, and you actually don't need to bother too much. On the large model, there's some scaling laws, and there's a bit of research, and it's kind of hard to know what works, what doesn't work. But I try to follow them a bit, because I'm like, okay, some people tried a few things, and I'm going to try to use, the same ratio they have of width versus depth. And then I have a report where I tried a lot of variants. Like transformers, there's like 100 different variants. So I tried a lot of them. And actually, some converge, some not necessarily converge better, but were more stable for some reason. So I tried a bunch of them, and I picked the one that worked the best.
Interesting.
Yeah, some for the activation, like the activation function, I don't think it matters a lot. I tried different. You have initially when you tried hyperparameters, like, oh, let me try different activation functions. It barely matters overall. Whatever you put it's okay. But yeah, maybe there's some advantages. I had one, maybe it had some noise, and I was like, okay, I'm gonna take the one that was stable. But maybe if I had just taken another seed, I would have had different results. So I don't know how much I can rely on some of the conclusions.
Cool. What do you attribute to the model's massive increase in popularity? Like I think we kind of noticed that our metrics for reports are getting messed up because there's so much traffic to your report. What do you think's going on?
Yeah, so I think somehow people think that model is new, but that model has been there for a year already almost. It's just like over time I worked on it, and little by little it became better. And actually the traffic, like the people using the model, people involved in the forums and talking about it, actually increased a bit over time. But I think when I trained a larger model, it reached like maybe a critical stage where suddenly it became good enough that good enough for like virality. And like I think some maybe YouTubers tried maybe for fun. They would put their name and they would put their name in different situation, like in the golf cart or whatever, and suddenly they would see their face and they would see something that looks like them. Not really, that was not very good, but that kind of looks like them, and they would put themselves in like the craziest situations. And I think they got excited about it, and little by little it amplified. Um, but yeah, it's just reached a threshold where it was good enough. What's fun is like the model is actually still training a little bit, so I'm curious of is it gonna be much better? And there's still stuff to improve. So it's interesting. It already reached a threshold that interests people, and there's easy ways to make it still better. So
How much data did you train this model on?
it's probably I would say around maybe 400 million.
Wow.
400, 500 million. But the data is actually very important, and there's some tricks here and there to try to make it work. When we train the model at first, and when you look at a lot of open source model that exist that you can play with, a lot of some problems that would happen a lot is like you would say, okay, I want a view of the snowy mountains. And he would draw maybe well the snowy mountains, and then on top of it, he would write Shutterstock. Or he would write Alamy, And the model had learned that, okay, an image typically needs to have a Shutterstock watermark or
Right.
Alamy, which was like kind of horrible, because that
Yeah.
image was like completely new, and you would have that horrible watermark on it.
Uh-huh.
So one of the first thing I did was like, okay, I don't want any of those images. I was like, how to avoid that? So it was a little problem, but for example, how did I solve that problem? Initially, I looked online, hey, how to detect if an image has a watermark or not. There was some things here and there, but it was not that great. And then some people were trying to generate data set with fake watermarks to try to detect it. And it was like already a big challenge to do that. And then I realized, okay, I can just remove all the images that have Shutterstock in the URL. And that problem is solved.
Right.
And actually that's the solution I took. And it works quite well because you never see a watermark.
Interesting. And uh, I guess how long does it take to train on 400 million images?
So I think the what matters the most when you have a lot when we didn't have a lot of data initially,
Mhm.
um, after a while the model overfits, and even more it's a bit smaller. The smaller model was what 400 million parameters, which is already quite big.
Mhm.
But after a while you overfit. Maybe I think after 5 or 6 epochs I would overfit, and typically that was the equivalent of maybe I don't know 2 weeks on one single TPU VM. Now, when you have like so much data, maybe more than what your model size can handle, I don't know if you overfit that easily. Maybe you can, but that's where you need to be very careful of having a good validation loss because there's that cool model that's called DALL-E, the Russian DALL-E, which is really really nice. But when you use it, it looks like it overfits. Um, it's a bit. I think it's not as good at composition, but it will make really nice images. It encodes the images also in a higher resolution than me, so
Mhm.
they have less of those artifacts. But sometimes you realize that you will type a description and it will show an image that it has seen before. So there's a lot of memory in that. So they overfit, and I think maybe they didn't have the right validation set. And there's a problem in that validation set too, which is if you just try to take random set for your training data and you call it the validation set, it doesn't work. And the reason it doesn't work is typically, let's say the Google logo is present on a ton of websites. So you have a ton of URL that will be unique, that will have that Google logo, but maybe the caption is different. So maybe if you try to be unique by image and caption, because it's okay to have a same image with multiple descriptions, but it's it's not good for your validation set because remember when you train it, the pixels see the previous pixel, so it will recognize the image, it may ignore the caption, and you will see your validation loss going down. But it's just because it doesn't care about the prompt, it just recognizes the images and just predicts it.
I see. That makes sense. So you're really training on just captions on images that you crawled on the web?
That's right. That's right.
I would imagine that would introduce all kinds of crazy artifacts. Like, is it easy to generate cool logos of companies?
Yeah, it can. So it's good at creating logos, and it's funny because it's something that made me happy a while back. So some person reached out to me like, "Hey, my mom started a new business. She couldn't afford to have a graphic designer. I just used DALL-E Mini. I gave her a logo. It was good enough for her business."
Amazing.
And I was like so happy that it was helpful in that way. So it can do surprising things, and like some things that I didn't realize would be possible, and the fact that it's open and that so many people can use it, that's
Mhm.
how I'm learning so much more. Like I realized I was barely testing the model before. I was putting a cat on a skateboard while people have those crazy prompts. Like my prompt, I thought when I was putting the Eiffel Tower on the moon, I thought I was creative, but like it's ridiculous in comparison to what other people do.
That's awesome. Do you have plans for what you want to do next?
Yeah, I think I have a lot of ideas. I don't know where I would go next. Obviously, like the model that use diffusion are very attractive because they do very impressive images. So it's definitely something I want to look at.
How does that work? I'm not for models that do diffusion.
Diffusion. So diffusion, the way it works, instead of predicting the image in one shot, because here you predict a patch and you just predict in a way in one shot, you iterate many times and you have an image that's like initially just noise, random noise. So imagine like random pixels, random colors, and you try to remove that noise little by little, and you go through it like 100 times or maybe 1,000 times, a high number of steps. There's ways to try to go through it a bit less times, but you go through the same model many times. Each time it removes a little bit of noise, and at the end it ends up to an image that's actually cool. So it's almost like I compare to me almost if it was like a recurrent model where you go through it, but the fact that you just remove the noise little by little, it guides it to a loss that's very friendly to train. Um, so it's like super promising, and it's like it's already proved to work very well with DALL-E 2 and Imagine. So that's something cool. The problem with those models is they're a bit more computationally expensive. So we still need a bit of research on how to make it more efficient, which I think is something interesting. So I'll probably look at that, but there's also my current model has many ways it can also be improved in cheap ways and fast ways. So maybe I'll try to do that or a bit, or fine tuning it on your own art or your own data. I think that could be pretty cool. And then there's people you can use the same model to maybe generate sound or music or video. You can do like so much with the same type of model. So it's pretty exciting what where it's going. I think it's going to go very fast too.
Is there any feature we could add to weights and biases to help you with your work?
To be fair, I feel like I've been using all the features with that project. I have the pipeline. The model is trained. I have the checkpoints. I resume from those. It's all tracked. When I do inference, I cannot do inference during training because it would be too expensive. I need to load that image decoder model. So
Mhm.
it would be inefficient. So I have another machine that does it. That's linked to the checkpoint. So I have that
Nice.
entire pipeline, that's set up, and that does regularly some inference and all. What could be added?
Are you using alerts like for when your model starts to go badly?
I should, because I look at the training way too often, on my phone. Like you have a little pause, or I go somewhere I'm walking and I'm checking quickly, is it still training, or did the TPU crash or not? Is the loss going high? Maybe alert would make me feel more relaxed.
Well, I have to tell you, it's been really fun to watch my friends who aren't in machine learning talking about DALL-E Mini and being like, "Oh, I know Boris. I know the guy that made it," and they're impressed. So, congratulations on
Oh,
such a successful model. It's really captured everybody's imagination.
thank you. That's fun. I like that. I think it's cool to see so many people using it. I was a bit scared that, because you could see it in negative ways too, or it's creating images. Um, but overall, the reaction has been pretty positive. People are happy that they can see through that model what are the limitations and biases and what can it be used for, and they can test it out themselves. And if I had to figure out the limitations and biases myself, it would be impossible. So I think it's actually really cool. And I like that, it's used for people who cannot draw at all like me. It's kind of cool because even if the image is not that pretty, it's still so much better than what I could do. But for people who are actually talented, I'm happy to see that some people, they use it as inspiration to take, hey, this was the output from DALL-E Mini, and then they use Photoshop and they do something crazy out of it. And I think it's really nice to see that it can also be used that way.
Awesome. Well, thanks so much, Boris. Great to chat.
Thanks. Awesome chatting with you.
If you're enjoying these interviews and you want to learn more, please click on the link to the show notes in the description, where you can find links to all the papers that are mentioned, supplemental material, and a transcription that we worked really hard to produce. So check it out.